Now let's take a look at two-phase mixtures. Consider a closed system containing saturated vapor and saturated liquid. The total volume is the sum of the volume of the saturated liquid and saturated vapor. The total mass times specific volume of the system, or average specific volume, equals mass of the saturated liquid times specific volume of the saturated liquid. The subscript F denotes saturated liquid, plus mass of the vapor times specific volume of the vapor. G denotes vapor, saturated vapor. MT equals MF plus MG, so MF can be written MT minus MG. Divide the equations by total mass. Average specific volume can be expressed as shown here. And from the definition of quality, quality is defined as the mass of the vapor divided by the total mass. And we use X to denote quality. So the specific volume is expressed in terms of quality. And rearrange the equations. We got this equation. And another subscript, VFG, denotes the difference between G and F, saturated vapor and saturated liquid. So specific volume was expressed in terms of quality. The same analysis can be applied to the specific internal energy and enthalpy. So the specific internal energy and enthalpy were expressed in terms of quality. Quality can be shown on the property diagram. X-axis is going to be the specific volumes, and y-axis going to be the pressure or temperature. And let's say this is point A, saturated liquid. This is point C, saturated vapor. The specific volumes at A is Vf, specific volumes at C, Vg. And we want to determine the quality at B. And the specific volume is V. The length between A and B is V minus Vf. The length between A and C is Vg minus Vf, or Vfg. So quality X is defined V minus Vf over Vg minus Vf. So the quality X is the length between A, B over the length between A and C. If the quality is 0, the state is at point A. If the quality is 1, the state is at point C. If the quality is 0.5, V, the specific heat should be in the middle of the horizontal line. According to the state principle for simple compressible systems, two independent and intensive properties are required to fix the states. In the two-phase vapor-liquid mixture, pressure and temperatures are dependent. What that means is at a specified temperature, the saturation pressure is determined, or at a specified pressure, the saturation temperature is determined. And we saw that, we confirmed that from the thermodynamic property tables. If the quality is known, we need to know either temperature or pressure to fix the state. Determine the specific volume of the two-phase liquid-vapor mixture of water at 100 degrees Celsius and a quality of 0.9. 100 degrees Celsius, we know that Vf and Vz. And we also need to note that Vf times 10 to the third is 1.435. So V can be expressed in terms of quality. Vf here is 1.0435 and we need to multiply by 10 to the negative 3 plus quality 0.9. Vg is 1.673 minus 1.0435 10 to the negative 3. So let's say this is 100 degrees Celsius and the quality 0.9 V is what we calculated at quality 0.9. Example 3.2. A closed rigid container of volume 0.5 cubic meter is placed on a hot plate. So here rigid tank indicates the volume of the system does not change. Initially the container holds a two-phase mixture of saturated liquid water and saturated water vapor at 1 bar with a quality of 0.5. After heating, the pressure in the container is 1.5 bar. Indicate the initial and final states on a TV diagram and determine the temperature at state 1 and 2. Mass of the vapor present at state 1 and 2. If heating continues, determine the pressure in bar when the container holds only saturated vapor. So we have a rigid container. No mass can go in or out of the system. It's a closed system. And rigid, so volume is fixed. And the initial pressure and the quality is given, and the final pressure is also given. To understand the process better, we can plot the process on TV diagram. And this line indicates the constant pressure. And this line is at 1 bar, and this line is at 1.5 bar. At state 1, pressure and the quality is given. We know that it's a mixture. And state 2, only the pressure is given, 1.5 bar. And state 3, it's completely filled with vapor. So quality at state 3 is 1. Let's write out what is known. State 1, pressure is 1 bar. Quality is 0.5. At state 2, pressure is 1.5 bar. And state 3, quality is 1. And we also know that since the volume is fixed and it's closed system, V1, V2, and V3 are all the same. First, let's determine the temperature at state 1 and 2. State 1 is in the saturated mixture. So we use table 8.3, a property of saturated water, and the first column shows the pressure. Since we know the pressure at state 1, we use this table 8.3. Pressure 1 bar and the quality is 0.5, and we know Vf and Vg. So we can calculate the specific volume at state 1. Specific volume at state 1. Vf1. And the quality is 0.5. Vg1. And this V1 equals V2 and V3. And V2 is 0.8475. And see the tables at 1.5 bar. At state 2, pressure is 1.5 bar. At 1.5 bar, Vf is 1.0528 times 10 to the negative third. Vg is 1.159. So 0.8475 sit in between these two numbers. So we know that state 2 is also in the saturated mixture. Since V2 is Vf greater than Vf and smaller than Vg at 1.5 bar, we know that it's under saturated mixture. So both state 1 and state 2 are in the saturated mixture. So temperature T1 is at 99.63 degrees Celsius, T2 at 1.5 bar, 111.4 degrees Celsius. Second, determine the mass of the vapor present at state 1 and 2. Since we know the quality of the state, we can calculate the mass of the vapor. Total mass of the system is volume divided by the average specific volume. Volume is 0.5 cubic meter divided by the specific volume. So mass of the system is 0.59 kilogram. So quality is defined mass of the vapor divided by the total mass. So mass of the vapor is quality times total mass. 0.5 times total mass. So this is the mass of the vapor at state 1. At state 2, we don't know the quality yet. So we need to calculate the quality first. Quality at state 2. So at pressure 1.5 bar, we can determine Vf and Vg. And the mass of the vapor at state 2 was determined. Lastly, we need to determine the pressure in state 3. And at state 3, we know the quality is 1 and the specific volume V3 is known. So at state 3, Vg 0.8475. It's at saturated vapor state. So go back to the tables and we know Vg is 0.8475 0.8475. So we need to determine the pressures when the saturated vapor Vg is 0.8475. So interpolate it to determine the pressure, and pressure at state 3 is calculated 2.11 bar.